Following on from video 1, these are the first 3 laws of Isaac Newton's amazing work. The first law is that a body will continue in a state of rest or uniform motion in a straight line unless impelled to change that state by an external force applied to it. Second law is that the change in momentum per unit time is proportional to the applied force. The change in momentum per unit time is proportional to the applied force and takes place along the straight line in which the force acts. We're going to see balls hitting off each other like this and stuff, and we have a straight line in here through their centers. The third law, to every action there is an equal and opposite reaction. To every action there is an equal and opposite reaction. So for now, just take these notes into your copies, and when we get into the questioning, we may come back and relate to these notes. So here's a note on Newton's first law. It's not much more than our definition of force. Okay, so there's not a huge amount. This is not like learn all these definitions off. We do have to know some definitions, not many though. It's hard to believe, but a ball kicked in the air would travel forever in a straight line if it were not acted on by a force. It's weight. So weight is the force due to gravity, which pulls it back to earth again. And we saw that in video 1, that definition of weight being the force that pulls something towards the center of the earth. So what about an external force? Well, what about a leather football sitting motionless in your garden? There may be all sorts of internal forces at work. It may be held together by the tension in the thread, the air inside is pushing at the leather from within, and the leather may be pushing the air back again. One stitch may be pulling at another, but these are internal forces. They're not going to cause the ball to jump up in the air, so they're not going to make the ball move. So what about external forces? Obviously you could run out into your garden and give it a kick. Okay, a strong wind could blow it. Kick, strong wind, and these are exerted on by agents other than the ball itself, namely air or you running out into the garden as a football player to give it a kick. So let's look at the notes on the second law. So I know I'm rushing through these, maybe 3 or 4 minutes of video, but you guys are going to pause these and put these notes neatly into your copy. So let's imagine we're going to call these masses m in these questions. So we're not imagining it, but what about if velocity is u here? So we have a mass m traveling with velocity u and acted on by a force F for t seconds. So you can see all my variables here: m, u, f, and t. So we normally use capital F and small letters for the other ones. And we also have v here for velocity. And this symbol here means is proportional to. And according to Newton's second law, force is proportional to the change in momentum per unit time. But momentum from before is this mu. Momentum is equal to mu. So the momentum after is m by the velocity, mv. So the change in momentum here is mv, what it ended up as, minus what it started at, mv minus mu. And this change took t seconds. So the change in momentum per unit time is this mv minus mu divided by t. This is the change in momentum per unit time. So you're going to write into your copy equals change in momentum per unit time, mv minus mu over t. So force is proportional to this. Force is proportional to mv minus mu over t. And that's what this is here. Just rub out that line so you can see it. Force is proportional to m. And we have, if we factor out the m times v minus u over t. Force is proportional to that. But what is v minus u over t from linear motion? That's acceleration. So we end up with ma, which is going to be our equation for force. And if we break it down a bit further, force is proportional to mass times acceleration. So it's proportional to k times ma, where k is a constant. And in our system of units, the MKS system, where a force of 1 Newton is applied to a particle of mass 1 kilogram, the acceleration is, according to the definition of the Newton, 1 meter per second squared. And putting these into the equation above, we get here this 1 equals k times 1 times 1. So therefore, k in our system is equal to 1, which means that we end up with this equation that we've written already. F is equal to ma, which we're going to see a lot. So if F is equal to 0, then A is equal to 0. And this is the first law, no force applied. The ball's just sitting out in the garden. So there will be no acceleration, and therefore the existing state of rest or uniform velocity in a straight line is maintained. Right, now let's look at, we can now measure the force due to gravity called weight. And we know that free objects fall under gravity towards the center of the earth. With this, my G is equal to 9.8 ms to the minus 2. So we have this mass here of m, and we have a falling with acceleration of g. So weight, my weight here, going down in this direction, weight is equal to mass times this acceleration of g. So we can say that this weight has magnitude mg. It's the force that's pulling it towards the center of the earth. This magnitude of mg, weight has this magnitude of mg. And it's just mentioned here that force equals ma represents the resultant or all the forces acting on the object. There may be many forces at one time. So that's the end of the second kind of introduction to Newton's forces. So make sure you have all these notes neatly into your copies before moving on to the third video.